The goal of this video is to work backwards from a given acceleration to determine what the position as a function of time must look like. We start with some acceleration, defined as the derivative of velocity with respect to time. To begin, we'll assume the acceleration is constant with respect to time, forming a flat line at a given value, in this case 5 meters per second squared. Even though the acceleration is constant, I can still write it as a function of time, because t to the 0th power is equal to 1, so writing the acceleration like this doesn't change anything. The acceleration is the derivative of the velocity, which means that the acceleration gives me the slope of the velocity curve as a function of time. Because the slope of the velocity is constant, the velocity must be a straight line with a slope of 5 meters per second per second. This is accomplished by simply adding 1 to the power of t. Because the acceleration only tells me the slope of the velocity graph, it is important to realize that any line with this slope will be a valid solution for the velocity function. That is to say, the acceleration gives me no information about where the velocity line should start. I need to represent this missing information as a constant in the velocity function, remembering that the derivative of a constant is 0. For the rest of this video, we will try to work with generic terms rather than specific numbers. So I'll represent the constant acceleration as simply being a. If I subtract the initial velocity from both sides of the equation, I'm left with a change of velocity as a function of time. Notice that acceleration is given by the y value of the plot. Time is given by the x value. Multiplying the two together will yield the area of the rectangle formed by the acceleration line and the x-axis, which is the same as the change of velocity. From here, we can attempt to perform the same operations to determine the position as a function of time. Velocity is defined as the derivative of position with respect to time. Once again, that means that the velocity function provides the slope of the position as a function of time. Doing the same trick as before, we recognize that t is the same as t to the first power, and t to the 0th power is 1. To determine the position, I'll add 1 to each of these powers of t. This will give me a power of t squared, and a power of t to the 1. Taking the derivative of this function would yield 2at plus v0. So to correct for this, I will need to multiply the at squared term by 1 over 2. Now, the derivative of my position function matches the velocity function. Once again, the velocity function only gives me information about the slope of the position. It gives me no information about what the initial position is. I once again need to fill in this missing information with a constant in the position function. Again, subtracting this constant from both sides of the function yields displacement as a function of time. This is a well-known equation for displacement that holds whenever the acceleration is constant. Rewriting at squared as a times t, I can again realize the relationship between position and velocity. Because the initial velocity appears to be 0 on this plot, the height of the line on the y-axis is given as at. The width on the x-axis is just t. Multiplying the two together yields the area of a rectangle, exactly half of which is beneath the curve. 1/2 base times height yields the area of the triangle under the curve, which is precisely what my displacement function gives. Don't let the v0 confuse you. If it is non-zero, there will be a rectangle beneath the triangle of height v0. Notice that the sum of these two areas is precisely the value of my displacement at any given time. Displacement can always be found by calculating the area formed by the velocity line and the x-axis. We will not always be so fortunate to have a constant velocity. Consider instead an acceleration that changes with time, like this one. A of t is equal to 5t plus 10. This is still just the slope of the velocity at any given time, so I can perform the same operations as before to determine the velocity. Term by term, add 1 to the power of t, and divide by that result. 5t to the first power becomes 5 over 2 t to the second power. 10 times t to the 0th power becomes 10 over 1 times t to the first power. Because I could add 0 to the acceleration without changing it, I need to add a constant representing my initial velocity. Once again, we will try to keep our solutions generic. Here again, the 1/2 bt squared term represents the area of a triangle, and the a0 t term represents the area of a rectangle. The sum of these two areas is the area formed between the acceleration line and the x-axis and is equal to the change of velocity as a function of time. From this velocity function, we can determine the position function. Term by term, add 1 to the power of t and divide by that new power. 1/2 bt squared becomes 1/2 bt cubed, divided by 3, which is simply 1/6. a naught t to the first becomes 1/2 a naught t squared. v naught times t to the 0th becomes v naught times t to the first. And I have to add a constant representing my initial position. The area formed between the velocity line and the x-axis will still give my displacement as a function of time, although it is harder to see now that the area does not form simple shapes. In mathematical summary, velocity is defined as the derivative of position with respect to time, which I can write as just x dot. Acceleration is the derivative of velocity with respect to time, v dot, which is the same as the second derivative of position with respect to time, x double dot. If we were to start with acceleration, we can define velocity as the antiderivative of acceleration with respect to time, which we write like this, plus a constant. Position, then, is the antiderivative of the velocity, which is the same as taking the antiderivative of acceleration twice. We can write those antiderivatives a little more cleanly by talking about the change of velocity and displacement. In general, to take a derivative of a function of time multiplied by some power of time, you simply multiply the function by the power of time and subtract 1 from the power of time. To take the antiderivative, you do this backwards. Add 1 to the power of time, then divide the function by the new power, and add a constant to fill in missing information. Please note that the antiderivatives are not always so straightforward.